Good day, students. Welcome to General Science 101. When we left last time, we were looking at the concept of work and power. We discussed with you that work is something when a force is applied, an object moves in the direction of the force. Like when I say that I take an object, I take it upwards. In other words, there is a change in height. I have done some work against gravity. Now, gravity is pointing downwards. I'm moving the object upwards. There would be a minus or a plus depending upon which direction I move, but still I have moved against or in favor of the force which was due to gravity. Therefore, work has been done. We did this concept of work with you and we moved forward. We also discussed what is power. Power we basically described as the amount of work done divided by the amount of time taken to do that work. We require this concept of power because it allows us to see how much energy we are going to consume to do a certain task, and if we want to do it in a shorter period of time, of course we have to consume a larger amount of energy. Coming back to the concept of work, basically unless we do work, we do not expend energy. Now, someone might ask, there are certain areas where we do expend energy without doing some work. Yes, there are certain areas. For example, I can hold this and do not move it. As far as physics is concerned, I'm not doing any work because the position is not changing of this object. However, my arms are getting tired. That means some chemical energy is being used up, and therefore this is consumption of energy. However, for our purposes, we will say, as far as physics is concerned, we have not done any work. Now, what we are going to do today is, we are going to move from the concept of work and power to look at energies, their types, how to utilize these energies to get some useful work out of it, and so on and so forth. Now, physics, like we told you, is a science which deals with measurement. We are comparing objects, we are comparing things, we are comparing lengths in order to find meters, how big is, how small it is. Same is the case. The second thing which physicists do is look at interplay of energies, and that is what we are going to do. We are going to discuss today. Now, energy in the broadest terms is the ability to do work. In other words, energy is required if we have to do any type of work. If we have to do any work, that means we have to move an object a certain distance, we have to apply a force, we have to use energy. And just like work, the unit of energy, of course, is again the joule. The unit of work we know is unit of force multiplied by the unit of displacement. That is 1 Newton multiplied by 1 meter would give you 1 joule of work. Larger units, of course, larger units of energy would be a kilojoule, or which is 10 to the 3 joules, or a megajoule, which is 10 to the 6 joules, or 1 million joules. There are different types of energies we know. We can look at a huge multitude of energies. Just to name some few, we have kinetic energy, we have potential energy. Potential energies are further subdivided into gravitational potential energy or elastic potential energy. We have chemical energy, nuclear, heat, sound, electricity, so on and so forth. When we look at all of these energies, we have, as we go along, we will find that our intention is that we have to change one type of energy into another type of energy, because some types of energies are more useful to us than other types of energies. Now, what we are going to do is look at these energies in a different perspective. We are going to look at them individually as well as collectively, because what we are going to do is we are going to try to move from one type of energy to another type of energy. And the way we to move it is basically a statement which is made that energy can be converted from one form to another form of energy. So if you have one type of energy, you have the ability to transform it into another type of energy. And from this we come to a very important law in physics, which is the law of conservation of energy. I'll give you the broad statement right now, and we will discuss the statement throughout this lecture as we look at different energies and how we can change one type of energy into another type of energy. The law of conservation of energy, as majority of us know, and as in textbooks it is stated, it is energy can neither be created nor can it be destroyed. It can only be converted from one form into another form of energy, of course. Now, in order to look at it more detailed, let us first look at mechanical energies, because we are coming from the concept of work, where we looked at the two types of work we did. We looked at the kinetic energy, and in other words, we looked at force and distance, and other work concepts. Now, whenever we are looking at the kinetic energy is the energy which an object possesses because it is moving. And kinetic energy is normally defined as the mass of the object multiplied by the square of the velocity divided by 2, and we are going to derive this relationship as we move along. The other type of mechanical energy we know is the energy an object possesses due to its position. For example, you have a brick which is lying on the top of a roof. If it falls, because it is under the action of gravity, it is going to move down, and if it hits the ground, of course, it is going to do some damage. And therefore, the energy which that object possesses because of its height is potential energy. Another type of potential energy is elastic potential energy. For example, I have a spring with me. Now, if I stretch the spring, this has got energy, it has a capacity to do work, because if I attach the spring to someone, it is going to contract, in other words, going to have a force which is going to make it squeeze that object, and in other words, apply a force. So when I stretch this means this now has stored elastic energy, which can, of course, then give us some work. We would say this is elastic potential energy, and we will discuss that as we go along. Now, let us do a simple derivation and try to see that how the formula for kinetic energy is attained. If you look at our earlier lectures where we did the three equations of motion, we have the third time-independent equation, which says the final velocity squared minus the initial velocity squared is 2 times the acceleration multiplied by the distance traveled. Now, let us assume that an object starts from rest and attains a certain velocity v. Therefore, the initial velocity would be 0, and the final velocity, of course, would be what we have attained. Let us say that it is v. Now, acceleration is defined as force divided by mass. Putting this value of acceleration into the third equation of motion, we find vf squared minus vi squared is 2f by m multiplied by s, or force into distance is going to be half m vf squared minus vi squared. Now, like we supposed in our problem that the initial velocity was 0. Therefore, vi, of course, becomes 0, and we have that the kinetic energy is 1 over 2 mvf squared minus 1 over 2 mvi squared, because that is what we are saying is force into distance is work, and because this work is ability, because the object is moving, therefore we say it is kinetic energy, and kinetic energy therefore is half mv squared, which is the relationship all of us know. It is a very simple derivation, and let us try to apply to a problem and see what we get. Let us say we have a fast bowler who is bowling a cricket ball of mass 0.25 kilograms at a speed of 20 meters per second. What is the kinetic energy of the ball? The data which we have is, of course, listed. We have the mass of the ball at 0.25 kg. The fast bowler is bowling at 20 meters per second. The formula which we are using is going to be half mv squared. The kinetic energy, of course, is going to be 1 by 2 multiplied by 0.25 multiplied by 20 squared, giving us 22 is 400. 400 into 0.25 divided by 2 is 50 joules. So the kinetic energy which the fast bowler is going to deliver is going to be 50 joules at that speed. Now, if we look at a slow bowler is, let's say, our slow bowler is bowling at half the speed, at about 10 meters per second. So our data again is the same. We have a mass of 0.25 kg. We have a speed of 10 meters per second. Now, the kinetic energy of the slower bowler, of course, is going to be half mv squared. In case of the slow bowler, it is half into 0.25 into 10 squared, giving us 12.5 joules. Now, this tells us that as because the kinetic energy is proportional to the square of the velocity. Therefore, if the velocity is decreasing, therefore the kinetic energy is decreasing at a faster rate. Let us look at the relationship for the potential energy. Now, potential energy, basically, again, we look at the general relationship, work is force into distance. And because energy is the capacity to do work, we say energy is also force into distance. Now, when an object is moved in gravity, we have the force, which is the weight of the object. It is moved a certain distance, s. Therefore, the energy which we have available is mg multiplied by s. In this case, it was the height. So we would have the work is equal to mgh, or the kinetic energy would also be equal to mgh. So what we have just looked at is that we have two mechanical energies. One was the kinetic energy, one was the gravitational potential energy. We have just derived their two statements, and we have stated that yes, we can mathematically derive the relationships and get that answer. We have kinetic energy is equal to half mv squared, and gravitational potential energy is mgh. The other types of energies, large number of energies, let us look at a few. We have chemical energy. When we say we have chemical energy, it basically is the energy which is inherent in the chemical bonds which are available in a substance. Let us say we have wood, then the energy is stored in that wood due to the bonding of the different carbon, hydrogen, and oxygen molecules. And when we burn that wood, these molecules dissociate, and the burning process releases energy, which is heat. Chemical energy is also present in, let's say, a battery. You have rechargeable batteries, you recharge them using electrical circuits, and then you reuse them when you put them in your mobiles or wherever they are required. So chemical energy is stored. When electrical energy is converted to chemical energy, it is stored in the battery, and it is reused when you are using that battery. So chemical energy is one type of energy. So any energy which is associated with the chemical process is known as chemical energy, and it basically has a concept which does not link directly to work, but it has the capacity to do work, because one would say that you have a battery, the battery is not moving. However, the battery can make something else move, and therefore we say this energy is stored in the chemical systems, which we can later on use as perhaps an electrical system or perhaps in the heating system. Like we said, we have elastic potential energy. That is a potential energy which is present when you stretch a spring or you compress something, and it is allowed to expand again. So that is elastic potential energy. It is again because of compressing a spring, we provide it certain substance, certain something, which then it has the capacity to re-expand and hence do some work. So we say this is elastic potential energy. Like we already have discussed gravitational potential energy, that is basically the energy an object possesses due to its position. This object will have a higher energy, this object will have a little lower energy. Of course, because we discussed chemical energy, we say we have also electrical energy. Electrical energy is produced basically in the coils of a generator. When you try to turn the generator turns in a magnetic field. The coils then have a current in them, which we say is electrical energy. You can also say electrical energy is produced as part of a chemical process in a battery. Now we have electrical energy, which then can be transmitted along wires and do work wherever we want to. Whether we convert this electrical energy to heat energy or into some mechanical energy, like in a generator, like in a motor, or perhaps in a fan, air conditioner. So electrical energy can be converted to some useful work, and therefore we say it is a source of energy. It is an energy which we can use. Other types of energies which we say sound. I'm standing in front of you, producing some noise. We say sound energy moves on, goes and enters your ears, interacts with the diaphragm, and you hear me. In other words, the sound which I am producing is being transmitted and reaching you as sound energy. So we say this is also another form of energy. If we have two magnets, and one magnet is going to attract the other magnet or repel the other magnet, so we say these two magnets can also possess energy, magnetic energy, which can be because they have the ability to interact with different objects, attract them or repel them, and therefore because they can exercise force, they have some energy available. You also have electric potential energy. Sometimes you have two charged objects. When you have two charged objects, again there is a force of attraction or repulsion between them, depending upon whether they are like charges or unlike charges. And therefore you can also say these would have electrical potential energy. Of course, not forgetting the major source of energy on this earth, that is the sun. Therefore we have lots of energies which are associated with the sun. The obvious answer being we have solar energy. So whenever the light and heat comes from the sun, it makes some changes, does some work on the earth, and we say solar energy is also an energy which can do work for us. Now, solar processes create a lot of atmospheric disturbances. We have tides, we have winds, and therefore we have tidal energy and we have wind energy. Another source of energy which is present in the earth is the geothermal energy. This is energy which is present in volcanoes. You can get in volcanoes, geysers. This is present inside the earth. The earth core is molten like we know it now, and therefore this is an energy source which is available and evidence of which we have whenever a volcano erupts. There are certain power plants in the United States, Canada, and Japan which are harvesting this energy to produce electricity. Therefore, this is also a source of energy or energy which is available to us and we can use it. Now, when we look at sources of energies can be moving objects, it can be fuels, it can be wood, oil, gas. As fuels, we can say these are sources of energies. We have falling objects, which is again a source of energy. We use falling objects like in hydropower projects. Water falls, it turns the turbine, and we convert the gravitational potential energy of a hydroelectric power plant to produce electricity for us. We have solar energy. You can have solar panels and run your batteries on that. You can have batteries, of course, which will run different appliances. You have nuclear energy, which is the energy present in the nucleus, which we harvest as we go along. And like we have said, you have also geothermal energy. Let us pose a few questions. Let us show that in order to convert one form of energy to another form of energy, these energies should have something similar. And in physics, if two types of energies can be shown to have the same units, we can say they are interconvertible, at least mathematically. Now, let us see that whether we can show that two types of energies and work. The energy which I'm going to look at is kinetic energy, and I'm going to look at work, and I'm going to look at the potential energy and see if they have the same units. Now, if we remember our discussion on the base system units, we said whenever we have a quantity, we can always look at its units in the SI system. For example, we have the kinetic energy. Kinetic energy formula is half mv squared. If we substitute the units for the quantities there, half, of course, is a number, therefore it does not have a unit. The unit of mass is a kilogram. The unit of speed is meters per second. Substituting it in the formula for kinetic energy, we say the kinetic energy should have a unit which is kilogram meter per second squared, because we have velocity squared, giving us a unit of kilogram meter squared second minus 2, or kilogram meter squared divided by second squared, which we say is the unit of kinetic energy. Now let us look at the unit of potential energy. The relationship which we are using for potential energy, that PE is equal to mgh. Now m is mass. The unit of mass is, of course, kilogram. A is acceleration. The unit of acceleration is meter per second squared. H is, of course, length, again distance. The unit, of course, would be meter. If we rearrange them, we find it is kg meter per second squared multiplied by meter. So I have kg meter squared divided by second squared, giving us an identical unit to kinetic energy, which is kg meter squared second minus 2. Let us look at the unit of work. The unit of work is defined as force into distance. Of course, we always say in the direction of the force. Let us break them up. Force is equal to ma. So work should have units of m, a, and s would be the kilograms, meters per second squared, and meters giving us again the units kg meter squared per second squared, or kg meter squared seconds minus 2. What we find is that the unit in kinetic energy, potential energy, and work have the same SI nomenclature, and therefore we say the units are the same, and therefore we can convert one form of energy into another form. How we convert it is, of course, a different matter, because some energies are easy to convert from one form to another, whereas it is more difficult, more expensive to convert other types of energies into useful energies. Let us look at the types of energies which are created or required when we use fuel in an oil-fired plant. You have a power plant which is producing electricity. It is burning fuel. So what are the energy changes which are required to produce electricity from fuel? Now, in a fuel, first step, of course, is the oil or the gas which we are using in the boiler is being burnt. So you have chemical energy which is in the oil being converted to heat energy. So chemical energy is burnt, you have something fuel which is burnt, and heat energy is released. The heat energy is then transformed into internal energy. In other words, water which we have there in the boilers is heated and it is converted to steam. Therefore, because there is no net movement of water, therefore we say the internal energy is increasing. We will discuss exactly what internal energy means as we go along, but for the time being, let us say the temperature of the water has been raised from one level to another level, so its heat energy has increased, it has become hotter. So in the first step, we had chemical energy being converted to heat energy. Then we have the heat energy is being converted to internal energy. The temperature of the water is being raised. It is being converted from water into steam. Now, the steam or the internal energy of the water then drives the turbine. In other words, the internal energy is being converted into mechanical energy or kinetic energy because the turbine is turning. Now, inside the turbine, of course, when a coil is made to move in a magnetic field, it produces electricity, or in other words, mechanical energy is being converted to electrical energy in the generator. So we have got distinct steps in this conversion. We have the fuel being converted to heat, the heat being converted into internal energy, the internal energy to mechanical energy, and mechanical energy to electrical energy. All of these are different types of energies like we discussed, and we are interconverting one form of energy into another form of energy. Now, this will also tell you that if you are going to convert the first thing, that is the energy stored in the fuel, into electrical energy, you need intermediate steps. You do not go directly from fuel to electrical energy. There are some interconversions which do not require intermediate steps, but there are others which do require us to move from one energy to another energy, and therefore to a third energy. And as we go into further details, we'll find that some processes release more energy, they are more efficient, and some processes are less efficient, they release less useful energy. Now, when we lift an object, let us say from here to a position B, the question is, do we do work? Now, if an object gains potential energy, have we done any work? The answer to this question is very obvious. Yes, we have done work because we have moved a certain distance against a force. The force in this case being the force of gravity. So we have applied a force, we have moved a certain distance, work has been done. So if we move an object from the surface of the earth to a height h, we have done work. We have provided work to the system. We will look into this from another perspective. If I leave this object from here, it falls to the ground. Now, this object is doing work for us. So, by saying the ground is to be at a zero potential and this is to be at a higher potential, whenever we do work on the system, the work is negative. And whenever the system does work for us, in other words, I don't do anything, the object falls on itself, and as a consequence, I can gain energy out of it, we say work is positive, because I am the system who has to get work out. So useful work always is positive, and if we are made to do some work in order to raise an object, we are working against gravity, so the work is always negative. We are losing energy. So the concept of positive and negative work basically is work is always positive if the system provides the energy, and it is always negative if we have to provide energy to the system to make something to happen, for some work to be done. Now, when we looked at conversions, we saw there were two types of conversions of energy. One was in which work was done, and one in which work was not done. There is a slight difference. We have a difference between working and heating. When you heat an object, you do not do work, because all of the energy which you have provided changes into internal energy of the system. For example, I have an object. I raise the temperature of this object a slight amount, let's say about 10 degrees. The object does not change. It does not change its position. It does not gain any speed. Whatever is happening in the internal molecular or the atomic level. Yes, the atoms start vibrating more. The object might expand a little bit. Yes, we would agree to that. However, from our concept of work, for work to be done, a force has to be applied. The object has to move a certain distance in the direction of the force. So per se, work has not been done whenever heating takes place. For example, you boil water in a kettle. The kettle is still there, even though you get hot water out of it. Therefore, per se, work has not been done as in physics. However, in case of a pendulum, you have a pendulum which is oscillating between 2 points. You have potential energy, which is converted to kinetic energy, which is reconverted back to potential energy. In this case, work is being done because the force is there. It is the force of gravity, and the pendulum is working against that force. Therefore, you have two different types of energy usages, one which allows us to do work, the other in which work is not done. The area in which work is not done, we normally say heating has taken place. Now, there are certain processes which we say are reversible, and certain processes which we say are irreversible. For example, if an object, in case of a pendulum, you have an object which is oscillating between 2 points. So it has potential energy, which is converted to kinetic energy, which is converted back to potential energy. So we have an interconversion of potential energy into kinetic energy without any apparent loss of energy. Therefore, we say this process is reversible. Just like in a spring, I compress a spring, and the spring has the ability to come back. In other words, whatever work I have done on the system can give me the same amount of work back. The spring is compressed. The spring on its own can re-stretch back. Just like if I stretch a spring, I do some work, I release it because of the potential energy of the spring, it will come back to its original position, and therefore we say this process is reversible. You have also reversible processes in rechargeable batteries. You recharge the battery on using an electrical circuit, and when the battery is fully charged, you can use it to do your useful work. You can use it in your mobile phones or to run a children's toy. So whenever you're using it to run a children's toy, a force is being applied, it is moving, so you are getting useful work out of it. So this is a reversible process. Electrical energy is stored, electrical energy is given back. We are not looking at whether we get the same amount back or same not or not. That basically comes in the realm of efficiencies. Now we have areas in which loss is irreversible. When we rub two things together, friction. In other words, the energy is lost totally to the surroundings, and we cannot recover it unless we use a very extensive, expensive method, which might inevitably lead to more usage of energy than we can actually recover from whatever has been lost as friction. Because when we are rubbing two things together, there is some wear and tear, heat is being produced, and that heat is being lost to the surroundings. Because it is being lost to the surroundings, we say this process is irreversible. When you burn wood, you are using up the chemical energy which is present in the wood, and you're releasing it as heat. Now, it is highly impractical to use that heat to recreate the wood. That is why in that scheme of work, we say this energy is irreversible, or this is an irreversible process. So we have looked at two things. we have looked at the interconversion of energies, we have looked at processes which are reversible and which are not reversible. And energy, of course, we will now, with the modern day thinking, we also say that when we look at mass, there is a process in which mass can be converted to energy. And a reverse process is also present in which energy can be converted to mass. Therefore, we can also consider matter or mass to be a form of energy. Whether we can harvest this energy or not is, of course, a different debate. The relationship with which we say that energy and mass are interrelated is given by Einstein's famous equation, E is equal to mc square, where m is the mass, c is the speed of light, and c square. If we look at the units of E is equal to mc squared, we find mass has a unit of kilogram, speed of light, because it is speed, it is meters per second squared, and the units you get is kg meter squared per second squared, or kg meter squared second minus 2, which is the same as joules. Therefore, like Einstein stated, we can do this. We can change matter into energy, and we can reconvert energy back into matter, which, of course, has been in the realm of science fiction for long. But, of course, with the advent of modern physics, it has been done, and we've had nuclear energy, of course, which we get is based on this equation, and we have processes which are reversible too, but we do not count this as a reversible process because the technology is still not there to reproduce or use energy to produce matter at a larger scale. Energy has been used to produce matter at the atomic scale. You can produce electrons or protons or antiprotons in accelerators, but that is something which is beyond the scope of this course. Let us look at another classification of energies. We will not say it's a different type of energies. This is a classification. Some energies are termed as renewable, and some energies are termed as non-renewable. There is a large debate going on these days to look at renewable sources of energy, because these energies are replenished over a period of time, and therefore they can be reused again and again. Now, renewable sources are those which can be replenished in a finite period of time. The renewable sources, for example, solar energy, every morning the sun rises, every evening it sets, the next day the sun rises again. Therefore, this is an energy which is available day in, day out. It is available on Monday, Tuesday, Wednesday, Thursday. Unless something happens to our sun, it is going to go on within our lifetimes. And therefore, this is one energy which we can use again and again and again without doing any additional expense. So if you have a solar panel set up on top of your house, that solar panel is going to provide you energy every day, and the only cost which you are going to do is going to be on maintenance. You have hydro sources, you have different dams. The dams, it rains, the dams fill up, and they generate electricity as they deplete, and the next season again you have rains, the dams again fill up, and you have again energy available from these hydroelectric plants. Tidal waves, ordinary waves, wind, these are all energies which are available again and again and again without any input from our behalf. Rechargeable batteries, again, you recharge the battery, use it, when it depletes, you recharge it again. These are all renewable sources. Non-renewable sources, sources which become depleted once you use them, like oil, gas, wood, coal. You pump out oil from the ground, you use it to provide you some energy, let us say in your motor car or perhaps in your power plant. That now oil is being converted to heat. It cannot be reconverted until millions of years take place, and oil is reformed as part of natural processes, that you have trees or plantation which is under pressure, partially decomposed. It's a long process, and in which oil is formed. It normally takes a couple of million years to convert decomposed material back into oil. And it is a natural process. It takes a very long period of time. So we say it is not a finite time, and these resources are being depleted. Because they are being depleted, we say they are non-renewable sources. Now, some of these non-renewable sources can be counted as renewable. One of the sources which we normally list as non-renewable, for example, wood, can be counted as a renewable source if we have sustainable agriculture. For example, we have an area of land where, let us say, we have divided it into 12 parts. Every year we plant one area of trees and we harvest the 12th area. So after 12 years, we have the first plot is ready to be reharvested again. So we have a cycle in which we plant one year and the same year we harvest a different area, and it is rotated. So this is a scheme of sustainable agriculture, sustainable wood supply, and you can always have a regular wood supply. But however, in this case, you have to be careful that it is a limited supply. You cannot over-harvest it, because if you over-harvest it, you are going to deplete your resource. Another area which we can see in this is perhaps the sustainable agriculture system is when you plant cotton. You are planting cotton, plantation is done, you are harvesting it, the buds are harvested but the stalks are left and they are used for fuel, and this is repeated again and again and again. Every season you have a new crop of cotton, new harvest of cotton is taken away and the stalks are used as fuel, and that fuel can be used, collected and used to produce energy in other forms, perhaps for cooking or perhaps to produce electricity. One other example can be the sugar industry. The sugar industry, you have every year the plantation of sugar. The sugar mills use this sugar cane, you crush it and you take out the sugar, and quite a lot of wastage is left. This then is burned in boilers and the sugar industry produces electricity. So you have a sustainable system here, that every year a new crop comes in, every year you do the major work which the industry has to do, and that is to produce sugar, and the secondary byproduct, which is that you have the sugarcane wastage left over, which is then used to produce electricity. When we are looking at mechanical systems, the one thing which we have to be really clear about is that the total energy of a system does not change. Let us look at a mechanical system in which the total energy of a system would be the sum of the kinetic energy plus the potential energy. The example which we can quote is, when you have an oscillator, you have a pendulum which is oscillating between 2 points. Potential energy, kinetic energy, potential energy, kinetic energy, potential energy. This is a conversion. So you have a system in which the potential energy is being converted to kinetic energy, is being reconverted to potential energy. So the mechanical energy is there. One mechanical energy which was potential energy changed to mechanical energy which is kinetic energy, rechanged back into mechanical energy which is potential energy. Now let us see if the sum total energy remains the same or not. Like I've said, the total mechanical energy is going to be the sum of the kinetic energy plus the potential energy. Now, let us look at an object. It is available on your slide. We have an object which is placed at A, it moves to B and moves to C. So you have an object which is moving under gravity from A to B to C. Let us look at the three positions. At A, the kinetic energy, Ke is equal to half mv squared. However, as the velocity is 0, the kinetic energy at that point would be 0. The potential energy at that point, because at point A, would be equal to mgh. So the potential energy is mgh, and the total energy would be the sum of kinetic energy plus the potential energy, which is mgh plus half mv squared. Half mv squared, of course, we've said, already stated, is 0. Therefore, the total energy is equal to mgh, which is the potential energy of the system at point A. The object has moved a certain distance, x. So the energy at that point would be the sum of the two energies. We have now the two energies at the point B, which is the intermediary point. You have the kinetic energy here is equal to half mv squared, but what is the velocity? We calculate the velocity from the third equation of motion, which is vf squared minus vi squared is equal to 2gx. or in other words, the final velocity is going to be equal to 2gx. Vf squared is going to be 2gx. So the kinetic energy, substituting this value into the kinetic energy relationship, we get kinetic energy is equal to half m multiplied by 2gx, or which is the 2's cancel out and are eliminated. So the kinetic energy is mgx. So mgx is the amount of kinetic energy that object has gained from this position to the intermediate position. And how much potential energy has been lost? The potential energy lost is going to be mgh minus x, because that much area has been depleted in the potential energy scheme. So the potential energy is going to be mgh minus mgx. Now the total energy, like we said, is the potential energy plus the kinetic energy. And as we can see, substituting the values, we find the total energy is mgh minus mgx, minus mgx, minus mgx, and plus mgx, of course, can be cancelled out, and we find that the total energy is going to be equal to mgh. Now, at the position C, that is the third position when the object has reached the ground, what is the kinetic energy at this point? We find it again from the third equation of motion, Vf squared minus Vi squared is equal to 2gx, and we find that the kinetic energy at this point now is going to be, kinetic energy is mgh. And of course, the potential energy is going to be mg into h minus x. At the position C, it is going to be, so kinetic energy is mgh, and potential energy when it is at the bottom position at point C, because the potential energy has now lost its height, the potential energy automatically becomes 0. So the total energy is going to be the potential energy plus the kinetic energy. And as the potential energy is 0, the kinetic energy was equal to mgh. We find the total energy here is equal to mgh. In other words, if we look at the three positions A, B, and C, we find the total energy at A was mgh, at B was mgh, and at C was mgh. In other words, the total energy has remained the same. The total energy at A has to be equal to the total energy of B, has to be equal to the total energy of C, which was the total energy in all case. However, the only change which has taken place is that the potential energy at A has been converted to kinetic energy at C, and the conversion has the same value, and in other words, like we have said, the total energy has not changed. Now, let us pose a question. I'm not sitting, but let's say if I was sitting in this chair and I've stood up, have I done any work? And if I have done any work, has there been any increase in my gravitational potential energy? And if there is an increase in my gravitational potential energy, from where has this energy come? Now, the answer is obvious. As my center of gravity has moved from something like this position, so there has been a change in my center of gravity. In other words, I have done work against gravity. In other words, my potential energy has changed. I have gained potential energy than from the position I was when I was sitting. So when I was sitting, I had a lower potential energy. When I am standing, I have now a higher potential energy. Now, where has this energy come from? Because the law of conservation of energy states energy can neither be created nor destroyed. So I have gained potential energy. I have to use some other form of energy to gain this. Yes, I have that other form of energy. I fortunately had some breakfast, and that chemical energy is stored in my muscles. And my muscles now converted that chemical energy into potential energy, and I was able to get up from the chair and stand in front of you. Whenever we eat food, we are converting the chemical energy on the food into chemical energy, which is then stored in the different organic systems which we have. Another simple example, that if you have got about 100 grams of ice cream, it should give us about 1 megajoules of energy available to us. Different books, depending upon what type of ice cream you eat, you might have a variation in this range. But normally, rule of thumb is that you should get about 1 megajoule per 100 grams of ice cream. Now we have looked at the laws or the rules which are governing the conversion of energy. Now there are two rules which govern the conversion of one form of energy into another form of energy. One is the law of conservation of energy. In other words, energy is conserved, that is, the total energy has to remain the same. The second is one form of energy can be converted to another form of energy, and neither is created nor destroyed. But however, you have to keep in mind that both of these laws work in unison. They do not work independently, but together, and that these laws are always valid in the physical universe, which we have shown, of course, in the examples we did with you before. Now let us look at some other examples and see what type of energy is stored in different systems. What type of energy, for example, is stored in a compressed spring, a moving body, falling water, hot cup of coffee, etc., etc. Let us look at these cases one by one and see what type of energy is stored in each and every of these systems. Now, if I have a spring, it is stretched. What type of energy does it possess? The only type of energy it possesses is elastic potential energy, which is the energy due to its elasticity. And if I compress the spring or stretch a spring, it has the capacity to do work, and therefore it has stored elastic potential energy. An object which is moving. You have a moving car, you have a moving truck, a cricket ball which is coming in, you are trying to attempt a catch and become the hero of that day. Yes, any object which is moving and which has mass would have kinetic energy. Water, which is stored in a hydroelectric power plant, what type of energy does it contain? Which is in a plant, because it is stored at a level and it flows down where it runs the generator. Therefore, the energy which stores is gravitational potential energy. And it is the gravitational potential energy which we are changing to electrical energy to do useful work for us. Of course, there are certain reservoirs which are not hydroelectric projects, but just for storage purposes. They do not store, they still have that stored energy, but we are not utilizing it. What we are looking at is interconversions of energy. Therefore, we would look at hydroelectric projects. So if you have a stored water in a dam, it has the capacity to run a turbine and hence produce electricity for you. What is the type of energy which is stored in a hot cup of tea or a hot cup of coffee? The energy which is stored in that is the internal energy, which is the inherent energy of the molecules. The molecules start moving a little at a higher speed, and that is the sum of the energies which are present inside that system. The tides of the ocean. In the tide, you can have the kinetic energy, potential energy, or both, because if it's a very high tide, the height would also give it potential energy, and the speed of the tide would give it some kinetic energy. Air moving in a particular direction would have wind energy, just like a current carrying conductor or a wire will have electrical energy. Can we create energy or can we destroy energy? That's the question. The answer to it is again very simple. Energy can neither be created nor destroyed. It can only be converted from one form into another form. Another question which we discussed is there any work done during the conversion of energy? Now, we said there were two physical processes. One process is in which a force was involved. If a force is involved, yes, work is done. Another process where there is a thermal energy or heat is involved. So you have two types of energy conversions. One is in which force is involved. That type of energy will do work. In which there is only heat exchange involved, is, as far as we are concerned in physics, will not do energy. We also looked at something in work. We said there is power. When the power was defined as work done divided by time taken. Now, because if we replace in that relationship work by energy, we find that power is energy transferred divided by time taken, or it is energy over time. Now, power can also be defined as work done over time taken, which is force into distance over time, or force into distance over time is, of course, speed. So power can also be defined as force into velocity. So we have another relationship which we have just developed, which is that power is force into applied velocity. And the unit of power, of course, is joules per second or watt, and 1 watt is defined as a work done of 1 joule per second, and the unit of that is the watt. Another thing which we can look at is the efficiency. We said that there are certain processes which are efficient and certain processes which are inefficient. what I'm going to do is start with the process of efficiency and see how far we can take it. Now, if we do apply some energy to a system, some energy of that system does useful work for us, whereas some part of a system loses energy. For example, if I'm driving in a car, then 65% of the energy which is used in a car is lost as heat in the exhaust, in the friction of the tires on the road, and only 35% of this is useful energy, which provides the kinetic energy for moving that car. So it is a highly inefficient process, and efficiency basically is defined as useful output divided by the energy into 100%, and that is the percentage efficiency you have, and that we are going to take up in the next lesson. In this lesson, what we have done is we have looked at energies, we have looked at interconversion of energies, we have looked at sources of energies. We have tried to give you a concept that energy can be converted from one form into another form. However, that cannot be, sometimes is not a direct conversion, and you have to have some intermediate steps. Like in a power plant, you have burning fuel. The fuel then is converted to internal energy of the system. That is, water is turned into steam. The steam then turns the turbine. In other words, you have internal energy being converted into mechanical energy. Then the mechanical energy is being converted to electrical energy in the generator, and you have a whole series of it. We looked at the concept that energy, because it can neither be created nor destroyed, can or should always remain the same. And we showed it in mechanical systems to you that the total mechanical energy of a system remains constant. We will continue more discussions in it in the next lesson. Thank you very much.